Welcome. This is the my line follow and Gyro my blocks video presentation for EV3 and Spike Prime. I've made a couple of updates of this. The original video was didn't come out as well as we had hoped from the call, and it was a little chaotic, so I decided to record a separate video. You can get all of the information for this video from the MAR FMAFL Director GitHub account. You can find a link for that on the FMAFLL Challenge info page. And do me a favor and please join the MAR Tools mailing list, because I don't want to keep sending out emails about this to the entire group. I don't want, if people aren't going to use it, they're not going to use it, and that's fine. And this way we can keep the discussion going. We also will be able to talk about it when we have the Let's Be Frank calls on Wednesday night. So this project is to provide a prepackaged set of tools that you guys can use. I have not provided any solutions for the current season. In fact, all of my testing was done on last season's mats and obstacles. I hope that teams will have an opportunity to kind of get a jump on this season and make it somewhat easier to program their robots and maybe learn something, hopefully learn something along the way. You're going to have to explain what you're doing to the judges, so you need to understand what's going on here. So I hope this presentation, as well as the code itself, will teach you how to do some interesting things. This project will not show you how to do any missions from the current season, so I don't want anybody to get worried that I'm going to be doing that. You will still, even though you'll have this software, which will help a lot, I think, you will have to still build your robots. You'll still have to build the components. You'll still have to put your missions together. You'll have to do the measuring. You'll have to do everything you need to do to make it happen. But these tools will make it a little bit easier to understand what's actually going on. And from the way I've been working, they are working really well. There's a few little caveats you have to worry about, but if you do what I'm telling you here, you should be in good shape. I want everybody to have a good experience. I want to share these tools. I want others, if you want to create tools, go ahead and create them, test them, do a presentation. And if you want me to put them onto the MAR tool site, I will. You will get full credit for everything that's going on, but this is a good way that we can add things. You may even have code that could do things differently than the way we're doing it here, and that's fine. In fact, I looked at a whole bunch of different ways to do line follow and gyro and turns, and some of them were very complicated. I didn't understand them, so I tried to make this so that it's somewhat easy to understand. Okay, installing all the files. This project will supply 3 demo programs. Actually, no, it's more like 5 demo programs. I should fix that. The ones you want to pick up are the EV3 Demo Final V2 if you have EV3, and the Spike Demo Final V2. The final versions of these, Demo Final and Spike EV3 Demo Final and Spike Demo Final, were the ones that I presented before, but these have a major upgrade that I think you're going to be pretty happy with. What I did was I created a my own block on the same system with the name of the file that I have, just with one block, and saved it. And then I copied this one over, and I was able to open it. Others who were at the seminar were like, "No, you don't have to do that." So I don't know. Do your best at getting it in there, but that worked for me. Create one with the same name and then copy mine on top of it. If you have a robot that is a basic design, like the advanced robot, you should be able to just take this and run it against last year's field, and it should work pretty well. Okay. Now, what you're going to want to do is create a blank or a clean copy. What I mean by that, you want to remove, I renamed all of the my blocks that were part of the demo with the word demo in them. So like there's the demo do truck, demo do bridge, demo, just erase those. If you want to keep them and look at them, that's fine, but get rid of them. you're not going to need them, and that'll give you space to make for your program. All of the my blocks will be off to the right-hand side, and then you can make space. Also, if you know you're not going to use line follow, for example, go ahead and erase all the line follow stuff, because it gives you extra room. It's up to you. But this way you can have a clean slate to work on, keeping all the my blocks in there that you want, and then building your stuff on top. Again, any problems, we will have, we will speak to people on the weekly call. All right, so what are we doing here? So the concept is to create a basic line follow. In other words, a basic piece of code that will do line following. And then the same thing with Gyro, the basic piece of code that will do Gyro. And then we will wrap we will wrap them into multiple variants. We're going to wrap them into a basic code that will run the basic code over a number of seconds. Run the basic code to a waypoint. We'll talk about what a waypoint is. Run the basic code to a certain distance. And the distance is accurate in centimeters and inches when you're using the V2 variant. And I'll explain why. I also show you the math. Okay. I find that if I read through the math and I understand it, I'm good. Okay. It took me a little while to get the math right so I could explain it to others. And I find it very helpful to do that because then I do understand it. I even have some advanced ideas I have at the end of stuff that I learned while doing this. All right, so let's set up the program. And this is true for EV3 or Spike Prime. So we're going to be using a lot of variables. And so you need these variables to do different things. And I'll clearly explain what they're done. And throughout this presentation, MB is going to mean my block. I didn't want to type my block 1,000 times. So both the Spike and EVMBs use variables for many purposes. And a lot of it's the same, whether you use the line follow or the gyro. You define these up at the top and then set the value at the top of the program so that you can affect everything that's happening down below. Some of these I used an underscore in front, and that was just a way for me to tell that it was used in the my blocks as a value and not something you can set, because it's probably going to get reset. I just decided that was a way to do it. In addition to that, when you look at the variable tab in Spike or EV3 Scratch, those variables will automatically rise to the top because they sort, because that underscore is lower than any of the characters in sorting. Okay. As a special note, when you're in Spike and you set a variable, when it's set, it shows up on this dashboard, which is to the right of the Spike screen, and you can actually watch those numbers change as the robot is running. So that's a lot of fun because then you get to see that. Now, here's some warnings. I tried to pass the IDs of the motors, AE or port numbers in EV3 as variables. And even though you could do it, it didn't really work well. I don't, maybe it was something else going on, but I just decided not to use them. So you're going to have to go through the code and set your ports for your motors manually. All right. So you'll have to look through the code and set those manually. Okay. The sensor IDs and the sensor values did pass okay, but I decided not to use the sensor IDs. At least I think I did. I may have made a mistake, but the sensor values certainly did make it through. Okay. So we have to define the environment. So I'm going to go through what the top of the environment looks like, and you can add all the other stuff in here you like. Okay. First, I set the variables and movement conditions, right? That's what we're doing up here. We're getting it ready. All right. The most important piece of this is calculating the circumference of the wheel. You can see it right there. Set drive wheel circumference to, and it gives a formula. That formula is how you convert the diameter, 8.8, times something called pi. Go look it up. Pi. That's pi. And that is a very exact version of pi. It turns out If you do that, you get a very good rendering of how far the robot will move, and you can measure it using a meter ruler. If you wanted to do this to inches, you would convert that 8.8 centimeters to inches and put it in there. And now you'd be using inches. And that works fine too. Okay. Now the whole key to this is we calculate something called distance per degree. Okay. Distance per degree. And the distance per degree is how far I go in one degree on the wheel. Okay, so its distance degree equals the wheel circumference divided by 360, because there are 360 degrees on the wheel. So imagine cutting a pie up into 360 sections. That's how big it would be. The edge of the pie, that's the distance that distance per degree would be. And so when you're running, we'll talk about that later, but I think you'll understand it. I also put in these two variables. You could remove them, adjust drive and adjust gyro. Adjust drive, I'll explain what those are, but they're set here so that we can use them, okay? And we'll talk about what they are later. And then we set motor motion to drive wheel circumference in centimeters. And we're doing that in case you decide not to use any of this line following stuff or line following stuff, and you just want to use something that moves the thing forward or does something using motion, then the wheel circumference and centimeters will be honored, and it'll go only that centimeter if you put centimeters in later in one of these movements. And it will be synchronous, and that's really cool. You can intermix this stuff as you wish. So if you find something too difficult using the tools that I've given you, you can just use the motion stuff to move it. And then I set my motion motors A and E, my two outside motors, left and right. All right. Now, when we're starting up, we're going to reset the angle, the yaw angle to 0. That's the gyro angle. That means left, right. Okay. Now, you may use line following and gyro and other stuff at different times, but up front, we want to reset it to 0 to say, okay, this is where we are. Now here you can see we have, the last thing is we have settings for the sensor. The line waypoint sensor is port B. The line follow sensor is F, and the midpoint reflectivity we'll talk about later. But this is where I'm setting the IDs of those devices into the code. And that actually does work. Okay. And then your code, my blocks or straight up code, goes right underneath. Okay. So this is the basic of everything right at the top. Okay, so now we're going to talk about line following for EV3 and Spike Prime. So let's just take a step back. What are we doing? So the line following idea is we want to bounce between the lines, okay? So using line sensors and sensing the reflectivity, not color, of the field, we want the robot to bounce back and forth between the dark lines and the white lines, but still moving forward. Okay, very important. That really sums it up. Okay, imagine you're in a wheelchair looking at a small spot between your feet. Close your eyes and see it. When you see a white or light area, I want you to push your wheels forward so you steer forward, but also steer towards the dark area. Okay? Not aggressively, but you steer towards the dark area. When you see a dark area between your feet, you push your wheels forward, but also steer towards the light area. That's it. That's how we do it. So how do we make the robot steer? How do we make the motor steer? We use different speeds on the left and the right motors. We're going to move the robots basically at the same speed, but if the left motor runs slightly faster than the right, you'll move forward, but you'll steer to the right towards the dark area. If the right motor is moved a little faster than the left and forward, you'll go forward, but the steer will be to the left. That's it. Now it's managing that bouncing between the lines that we're going to take care of here. Okay, so it's really not that difficult. All right. We also added a little wrinkle here to something called a waypoint sensor. Okay. So imagine the front of the robot has what we call, or I call, a line follow sensor, but it has a line waypoint sensor. And yes, I totally made up the second name. The line follow sensors sees the light reflectivity, right? Light and dark on the board. The waypoint sensor is looking for the dark waypoint reflectivity on the board. Only the dark. Now, you're only gonna do something with it when you want to, but it's reading it all the time, okay? But only when you want it to react will it. Now, the ambient light does greatly affect this, and you must test at your local competition to see what the light is like. I would create yourself a little My Block just to turn on reflectivity of these sensors, and then at the field you can check to see if your stuff is going to work. Now, what is a waypoint? Notice where the waypoints are on the field. I don't know if FIRST made these waypoints and said that's what they are, but I think they are, because look at where they are. Okay, I'm not going to talk about it anymore, but go back and look at where these waypoints are and why are they there. They're there because there's something there that the thing wants you to do, and we make use of that in the code that I have. Okay. Notice that the EV3 or the basic Spike Prime comes with only one lens sensor. You're going to need to use two if you want to use waypoints. Okay, so here is the line following demo block. Okay, all right. I'm using a couple of different ideas here. So what I want you to think of is use something to display in between each movement so you can see it change and you go, okay, now it's working. And you'll know when the code changed. It's very, very helpful as a debugging tool. Okay. Somebody said, oh, well, doesn't that slow the thing down? I'm not sure it slows it down that much. And it's really in between the lines, you're not doing anything major with it while you're actually running. That might cause a problem. It's only in between the lines when one My Block is done and the next one is about to start. Okay. So you can see what that looks like, huh? Essentially what this is, for example, the line follow to waypoint line is a custom My Block that I created, and it has parameters that you can pass to it. And those are speed, which in this case is 40, and something called correction factor. Ooh, let's not get crazy about that. All right. We're going to learn all about what I call correction factor of a value of 8. And you can see that the speeds and the correction factor and the distances are all changed here. Okay. And those actually work pretty well. All right. Now, one of the things about distance here is it's a little weird because you're actually trying to bounce back and forth between the lines. So the distance may not be exactly accurate, but it's going to be close. Okay. Unlike the gyro is very close. These are going to be, you can measure it out and try it and you'll be close. And then you make a small adjustment. Okay. Okay, so now here we go. We're going to run it. Now I want you to watch the behavior of the robot. Look at the debug and see what it says when it's doing it. Okay, I'm going to run it again. Now, if I was in a discussion with you all, I would ask you what's going on. But the W says it's looking for a waypoint. There it is. It hit this waypoint, right? So that's what that's doing. And then it went to S. It's going slow around a corner. We slowed the speed down, correction factor of 10, right? The correction factor of 8 up here made it go more straighter without bouncing back too badly. 10 is a little harder. It's going to bounce back. We want to make sure that it stays and it never crosses over the black line. Okay. And then I can go fast, and then I go slow, and then I go fast over a distance to the end. We'll do it one more time. I want you to look at the end there. The color of the field is darker, and the waypoints wouldn't work up there. You might be able to have to create your own waypoint variable, right? Value to say, don't look. We'll talk about that a little bit later. Here we go with the EV3. Okay. Now I'm going to run that again. This actually does use the waypoint, I believe, up first. And the colors go green for fast, red for slow. All right. And you notice in the middle when it's going fast, it kind of flies over the white line. That's because the light areas are considered light. So it's slowly bending its way back into the black line. And so we can go much faster. And you can control how much that is by changing the correction factor. You can really see the aggression here around this corner. Watch. See? Okay. So let's have a discussion about the different terms I'm going to be using. A light area. There's a light area. Reflectivity anywhere from 99 to 35. Those dark, see those green bushes to the right? Those are going to be dark. Those dark blue areas. And there might even be black areas on the field. And those are going to screw up the line sensor. So again, you might, if you're using a waypoint, you might have to create a separate variable to handle that. So it's looking for that. All right. The white area usually has a reflectivity of 99, between 99 and 80. Okay. The black line is going to be about 30. And that's for Spike. For EV3, it's a different number. You have to go and check. The waypoint lines have the same as the dark reflectivity of 30. Okay. So you might have to create a separate variable for that. I did not, but you would have to modify the MyBlocks to do that. Okay. So the ambient light definitely affects what's going on. The white and the black lines work fine. Sensing colors and areas outside can be tricky. The spike sensors I thought was somewhat better than EV3. I'm not so sure. But I think by creating a separate variable for a waypoint, you might be able to handle that. Okay. So as the robot and the sensor moves forward from light to dark areas, the reflectivity is going to change. In the light area, it might be 85 because it's partially in the white and partially in the light area. On the white line, it's going to be 99. In between the lines, the reflectivity might be 45. The black line, it might be 30. And again, this is all spike. Okay. Now, I created a variable called line midpoint reflectivity. Okay. And currently you can see that the piece of code down there has it set to 40. That was in the variables we had at the top. And what that says to the code is, think of it, I like to say, think of it as a bouncing ball. Okay. If the midpoint is set to 45, that means it goes to an area between the lines and then bounces off between the lines and then bounces off to the light area. If the midpoint is set to 40, it goes into the dark line a little ways, a little more, and then bounces off. We never, never, never want the sensor, the line sensor to cross the dark line into the other side. That is bad. All right. So we're going to create the basic line follow code. And here it is, right? So you create a new buy block, right? And you have, in this case, it's called basic line follow. You pass it a parameter of speed and correction factor, and we will discuss correction factor a little later. Okay. The next line is we want to capture the current reflectivity. So we have a variable, line follow reflectivity, all right? And we want to set it to the line follow reflected light, right? Line follow sensor, which we defined up top. We want to set that into line follow reflectivity. We do that because it's going to show up on the dashboard, and we can read it and see what it was. Okay. Now we're testing in the if statement. We're testing line follow sensor reflected light less than line midpoint reflectivity. Okay. So think of what that's saying. When the line follow sensor reflected light is less than the line midpoint reflectivity, then we're going to set something called correction to a correction factor, which you pass, times -2. Or else we're going to set the correction factor to the correction factor times 0.5. Okay? All right. Now that looks a little weird. Why aren't they the same? We'll talk about that in a minute. Okay? Having those different, where it says calculate on the left, calculate motor underscore correction. In the dark area, we're using the -2 because it means we're going to be more aggressive in our steering back towards the light area. Okay? And the 0.5 is for the light area. It means 0.5. It means when we're in the light area, we're going to go aggressively steering back to the dark area, or less aggressively steering. So less aggressively steering back to the dark area. This allows us to go faster in the straight lines and slow around the corners and stay in between these two white lines. Okay? If you remember the video from before, you saw as it went fast over the back, it looked like it was flying over the bar and came back down. That's because it was in a light area and it was a less aggressive to bring it back into the line. All right. Also, you can modify the global variable adjust drive. We apply that correction here. So if it's 1, nothing changes. If it's -1s, the motors will reverse, or the correction will reverse. And then when we put it to the motors, it will reverse. And again, this is useful if when you put in a positive speed into one of these things and the robot goes the opposite way, you may want to use this to flip that around, and that'll allow you to have still positive speeds even though the motors are flipping it around. So we'll fix that. All right. Finally, we set the left and right motors with different plus or minus corrections. Okay. So the left side gets speed plus negative correction, underscore correction, and speed minus underscore correction. All right. And we'll look at the math to see how it all works. It sounded kind of complicated, but it is not. All right. So now what happens if I don't use, like I hate to use all this complicated -2.59, right? What if I just want to use 1 and 1 and it'll just wiggle? We would call that a symmetric response or a symmetric correction. I'm using the same correction on either side, -1 and 1, right? Let's watch what happens. So what happened? It crossed the line. All right. The problem was we weren't aggressive enough to get out of the dark area so that we could get back to the light area, and it broke through to the other white line. So using the -2 and the 0.5 forces it to quickly get out of the dark area. That's the -2, and slowly out of the light areas. This allows us to turn at higher speeds. This is an asymmetric correction, which means it's not the same. As it uses 2 different responses in the 2 areas. You can test, and test some more. We're going to talk about correction factor in a minute. That has an effect on this too. Okay, so let's talk about that correction factor. So the correction factor is a pass parameter. I totally made that name up. It controls how aggressive you want the motors to swerve to the light and dark areas. Okay? It controls how aggressive You want the motors to swerve to the light and dark areas. If you're using a positive correction factor, the robot bounces between the upper white line, right, or area, and the black line. If you use in a negative correction factor, the robot bounces between the lower white line and the black line above it. Okay? That's it. That's what it's doing. The higher that number, the quicker it's going to try to get into the other area. Right? So you change this according to the conditions. Now, for example, in Cargo Connect, in that example below, why could we not use negative CF? I'm going to pause here for a second and you tell me. We couldn't use it because our robot, if it was too big, would crash into the side of the truck. And that would be obviously bad. Okay? But you can see from the videos that I did that it actually works and it does pass those. Okay? Now, the old way of doing some of this line following is the plain old setting and letting it just sit there and go back and forth. And you really weren't going very fast anywhere. All right? You could also set the CF high and use a slow speed and allow it to go all the way. But we're not doing that here. We're breaking these up into multiple steps, which I showed you was pretty easy. And you set the CF low when going fast and straight and the CF high when going slow around curves. Okay, so that's correction factor. All right, so now let's look at the basic line following. We're going to put it all together here, right? We're using the positive correction factor when the light is on the left and black line on the right, right? It steers, when it sees light, it steers right, slowly, slower than the other. I wouldn't say totally slowly, but slower than the other. When it sees dark, it steers left aggressively, okay? The variable adjustment, adjust drive set to 1 here for the calcs below. All that's going to happen at the end, if I set that to a -1, is it'll just flip the results to a negative, and it'll be the opposite reaction, which is what you want on the motors. Okay? So now, just let's look at this pretty simply. 1 is the past parameter up at the top. That's that speed parameter in the lighter color red. You would actually drag that down later on. You can see it down there at step 6 and 7. I pull that speed down and use it there, right? 2 is correction factor. You see the lighter red oval. That's correction factor. That's the value. You can see that it was pulled down and used in the code below. So I'm giving you a sensor light reflectivity, right? In the first line, I'm saying it's 99. That means you're right on a white line. You're on a white line. And the midpoint reflectivity is set to 40. That's the point where we want to say anything below 40 is dark, anything above 40 is light. So now let's do some calculations. So we take our correction factor of 10. This is on step 5. 10 times 0.5 equals 5, right? In each case, except for the last one. Well, let's just do the first one. 10 times 0.5 equals 5, right? So our correction is going to be 5, right? So we add that speed, 30 plus 5 is 35 to the left motor. 30 minus 5 equals 25 to the right motor. In your head, imagine what's going to happen if you're in the wheelchair and the left motor is at a power of 35 and the right motor is at a power of 25. You're going to swerve, you're going to go forward, but you're going to go slowly right to the dark area. That's the idea, okay? Just as you know, computers are nothing more than pushing numbers around. Really, that's what it comes down to. All right? I'll let you work through the other values or the other math. Maybe we could talk about the one at the bottom. The other one isn't too much different. It's 10 light sensor 50. 10. So the second one is 30 pass speed, 10 correction. Sensor is now 50, and midpoint is 40. So we're still in a light area. So all of the math is the same. We're still in a light area. Nothing happened. Okay, so we're going to still move right, but we're going to move slowly right to the dark area. That's kind of like what happened at that one video where it floated over the line and came back. That's what that effect is. The final one at the bottom is 30 for the speed, 10 for the correction factor. The light sensor reflectivity is 37, and the midpoint is 40. So we're now below the midpoint reflectivity. So now we're going to get 10 times -2 equals -20. That's our correction. Now we put it to the motors. 30 plus -20 is 10. 30 minus -20 is 50. What are we going to do? We have 10 on the left and 50 on the right. We're going to swerve aggressively from the left to the light area. We're going to get out of the dark area and get back to the light area. You got it? All right. Work through this and you can see it. This is simple math. I mean, but this is what programming is. It's all about setting these models up. That's what this is, a model, and how it reacts to the incoming information. Okay? Now, if you got that and you had fun with that, let's use a negative correction factor. Basically, it's going to flip the numbers around. Okay? -10 is my correction factor. That's if I have a black line on the left and a white line on the right. And you can try that. I know this year's game has a bunch of that stuff on there, so you might try and use it for that. All right. So we're going to go back here and we're going to use Spike Prime again. We're going to show you. Now, this is a robot that was a small robot built out of a Spike Prime basic kit. I didn't have the big wheels or anything, but I put one of those together to demonstrate all of this works. Now, notice how less aggressive in the straight areas and more aggressive in the slow corners. The difference here is the robot is lighter, so it reacts much more aggressive. Okay? See how aggressive it is going around the corners? Less aggressive going straight. But it still gets the job done. We're going to look at the EV3 again with all the nice knowledge you now have, all right? See how it floated over the black line there? Okay. So now that we have the basic line follow code, which is going to be down here, we're going to create our variants, okay? So the first one we're going to create is my block over time, all right? So when we create that my block, we create speed and correction factor, but we add another variable called time, okay? And essentially what we're going to do is we're going to continue to run this. We're going to reset the timer here, right? We're going to reset the timer there so that the timer's back to 0, and then we're going to repeat as long as the timer is less than the time we passed. That's pretty simple, and we're going to run this code. And we're going to pass speed down here and correction factor down here. Pretty simple, right? When we get to the end, we're going to go stop moving. That can't be that hard, right? So you're taking all of that somewhat complicated code and you're going to throw it in there and run it. All right, so that's that. The second one is we're going to be creating a line follow variant called to waypoint. So it's line follow to waypoint line. All right, same thing. We're passing speed and correction factor. All right, and in here, the first thing we're going to do is set the line waypoint reflectivity from the sensor. That's so it shows up on the dashboard. Okay, and then we're going to repeat until the line sensor reflection is less than the line midpoint line. Now, if you remember the discussion, I set the line midpoint line to a 40. The problem is some of the parts on the field are darker than that, and it may see that. They're not as dark as the black area, but they're darker than the midpoint line. So some of these may not work. So my suggestion is you may want to change this so that instead of using line midpoint reflectivity here, you might want to create a, a new variable called waypoint uh, midpoint reflectivity or maypoint, whatever you want to call it. And what it basically means is when it's less than this value, it will trigger and say, okay, I'm there, stop going. I didn't do that, but I think you could change that and fix it. Okay, so I think you may want to change that. So what is this is doing? It's repeating, it's setting it again, line waypoint reflectivity. It's setting so you can see it on the dashboard, and then it's calling the basic line follow code. That corrects the motors based upon where we are and sets the robot in motion. Okay. Okay. So now we have line follow variance over distance. Okay, over distance. Same idea. We're wrapping the basic line follow code into something that's going to measure the distance for us. Here's the speeds are transferred down, right? We're not using any of those variables, but we are using distance. So this is the interesting part. What is actually going on here, right? So we pick one motor to be the measure distance motor. That, in our case, is the A motor. This is some of the things you're going to have to change in your code between what I have on my robots and what you had. Okay. So we're resetting the relative position. EV3 uses a different term, but if you look at the EV3 code, you'll see it. Reset the relative position. And essentially, once we do that and we read that relative position, it's 0. Okay. You got it? So we're resetting it. We're saying, okay, we're going to start from here. Now, you run the repeat loop until, and read that line. Repeat until ABS relative position times distance per degree is less than the ABS of the distance. Forget about the line ABS. Let's just say when the relative position times the distance per degree is greater than the distance, it stops. So what is relative position? It's degrees. If I'm riding along and I make one revolution of the wheel, relative position is going to be 360 times the distance per degree is the distance the wheel goes in one revolution. Okay? Make sense? So think of it. The wheel is turning around once, and that gives me a relative position of 360 times the distance per degree, which we calculated right at the top, and we're measuring that against the distance. And this works actually very well. Okay? So now, let's talk about what we're doing here. Okay? Don't freak out. Anybody freak out. All right. First, we reset the encoder of the wheel to use for measuring, in this case, the A motor. It's the left motor. I'm a lefty. I chose the left wheel. Doesn't matter. Pick whichever one you like. Okay? The relative position comes back as degrees. Okay? We're using something called the absolute value function. It is used to convert the accumulated degrees and distance into positive values. It's actually distance from 0. Distance from 0. Okay? That's what it is. It allows this my block to work in plus or minus speeds, plus or minus degrees. Okay? Actually, I don't want you to give me plus or minus degrees. Give me positive degrees. Okay? We never want to see negative degrees, and plus minus distances. Okay? Very important. So even if you're going negative, my speed is going to be yes. Even if you're going, even if you're going negative on distance, I'm still going to see it as a positive because absolute is telling me from 0. How far are you from 0? And we don't care in the direction. Okay. So again, depending on how the robot is built, in fact, when I built that Spike Prime drive-through base robot and I gave it a positive power, it went in the right direction, but I don't know why. The degrees came back as negative, and it didn't care. This didn't care. It fixed it. So the relative position in degrees came back as negative. The ABS took care of it. It said, I don't care. I just want to know how far you're from 0. Okay. All right. We repeat until the accumulated degrees times the distance in degree is greater than the distance, right? Right. So it's the how much am I moving each degree? Once that's calculated over time, we're done. We're good. And that having a more precise version of pi is a good way to do that. Okay. So at the top, for example, we were using centimeters, the 8.8. It actually was an 88 millimeter wheel, and we can get that information from Lego, and it's 8.8 centimeters. Now, I didn't use a real good version of pi here, and I am recommending that we do it, so I may have to fix this slide. All right, but if we just, one revolution becomes the wheel diameter times pi. All right. Now, when you calculate that and you do the divide, you get the distance of degree on the second step. You can see it on the dashboard as it gets calculated. All right. If I was going to do this with inches, I would have to convert the diameter into inches. Now that 2.178 is actually from a 56 millimeter wheel. And why did I use inches? It's honestly because I lost the ruler I had, and I was like, ah. So I figured, all right, let me do it in inches. And that Drive Base 3 robot is doing everything in inches, and it worked fine. Okay. The wheels are smaller on that robot, 56 millimeters or 5.6 meters. I use Google to convert that to 2.178 inches. So the circumference is 2.178 times pi. Again, use the better version of pi. I didn't get a chance to change that. Okay. The robot motor has the encoder that will break it up into 360 degrees or ticks. Okay. The distance per degree, right? We multiply that. If you go back and multiply the distance per degree times 360, you will get the circumference. Okay. Now we're putting line following behind us. We're going to talk about gyro navigation. This is all very similar. So we're going to do a thought experiment. Put on very colorful socks. I was a theater major, so imagine you are sitting in a wheelchair looking down at your feet. Okay, those are my feet. All right. You see a line between your feet. Okay. Using your hands, push the wheels the same to go forward. What happens if they weren't the same and you drifted a little bit to the left? The robot yaw is now going to report a -1. What do I have to do to correct that? You can pause here and ask people in the class. Okay. What do I have to do here? I would use my hands to push forward, but put more push on the left and less on the right to go forward, but also steer the wheelchair back into the line. All right. If you only have to correct a little, you push a little. To correct a lot, you push a lot. We call that proportional control. Okay. Now, even though that is proportional control, we're going to change that up a little bit, and we'll talk about that in a minute. We use motor calculations to make this happen, just as we did in line follow. All right, so what is this line, and what are these robot degrees? Negative is a negative angle is to the left, positive is to the right. Be careful turning to or past -180. Okay, it's not a good thing. Go ahead and do it and see what happens. Now, if you use a negative speed to back up, you can use a negative speed to back up using gyro. And here again, ABS is your friend. But some people might complain, but what do I want to turn the robot around past 180 to complete my missions? Okay, why? I've seen it done. And the only reason I'm saying this is because I've seen it done. Well, one way you could do it is you could take your robot and back it into a wall at 90 degrees, either at the bottom or the top of the field, right? Square up your robot on the wall and make it flush. Then reset the gyro there at 0 in the middle of your my blocks. And now you have a new direction, and it's going back the other way. Okay? All the gyro my blocks will use the new gyro heading to do more missions and get you home. Now, that's the old way. This season, we actually can go off to the right. So I don't know if there's any reason ever to want to do a 180-degree mission or turn. Okay, so think of that. Okay, so what changes did we make to this? We made a couple of changes. One, here after the seminar, I realized that we really needed to have a way to accurately turn. So I created gyro turn to angle my block, and that's in there. All right. And it actually turns very well, and we'll talk about how it does that. And it's very accurate, pointing within plus or minus a 0.05 of the angle. And you can see where that is set. It's not a mystery. So I added this to the gyro to waypoint and the gyro to distant my block, so that when you now call gyro to distance, gyro by distance, you first turn to the angle. All right. It turns accurately to the angle before the gyro loop runs, the distance runs. Now, the result of this is the distance is very accurate because you're not using any of the distance measurement to turn the robot. The distance is now measured from where you start after you are turned by the gyro to turn by angle and then go. And it is very accurate because we're using a better, more accurate version of pi, and it works great. I've also added a new variable. I have to fix this. I didn't catch this. It's gyro turn speed max. Okay? Ignore what it says here. Gyro turn speed max will be used to give us the turning speed that we allow the angle to turn. Okay? And I'll show you where that's set and why we're doing that different from what happened in when I originally did it. Okay? So we're using a speed, a set speed. We're not using a proportional response. I'll explain why in a minute. All right, so here's the basics. We're going to wrap a gyro a gyro basic code into each one of the separate variants. We didn't create a separate basic my block. I did originally, and it didn't work as well. And I think it's because the robot was moving, and so it was missing. It was late on doing what it was supposed to be doing. So I decided to take that piece of code and just duplicate it down to all the variants. Okay. The gyro angle yaw left-right measurement on the gyro center is measured 0 to minus 180 is left, 0 to plus 180 is right. We already talked about some of this. Now, this is critical. When you power on your robots, you must let them sit quietly as they boot up. No bumping. If somebody's going to be bumping a table or something, put it on the floor where nobody can bump it. Okay? Put it on the floor. Let it boot up. Let it settle down. Okay? And don't even look at it. Don't look at it. Don't look at it. You get it, right? Don't go near it. And the reason is it's calibrating. The EV3 takes a lot longer to do this. And when it's finished calibrating, the gyro is good. Okay? But if you walk around moving it when you turn it on, the gyro is going to be drifting by the time you get to use it, and you're going to get crazy results. Now, when you actually run one of these using gyro, you're going to start the robot in exactly the same place and orientation every time. Use field markers to know where you are. Remember, we reset the gyro once to 0 at the beginning of each run. So 0 degrees is now straight ahead. Whatever straight ahead is, depending on how you have it oriented. Right? So the robot is designed to go fast in straight lines with little correction needed. Okay? We are still going to use our gyro to correct it, but it doesn't need much correction at all. Make sure your wheels rotate freely and are not rubbing on the robot. Add spacers to ensure it. Okay? Some people, especially in FRC, they're like, oh, don't worry about it. The software will correct it. It won't. Okay? It's not going to correct it. Okay? Bad is bad. It's got to be working well for the gyro to be able to do what it's supposed to do. And this is something I learned after many, literally 12 hours last Monday. When using the gyro and turning, try to turn relatively slow. If turning too fast and too often, the gyro will drift. Okay? And I can show it. I can show it happening. Okay? And it makes the gyro yaw useless. Okay? Now you can take the values I'm using and up them a little bit and see where you go. experiment a little bit. But at some point, and that's because your robot may be heavier, may be lighter, a million reasons why you need to do that. But experiment so you feel comfortable with it, right? Now, your starting position. Now, notice my gyro is an advanced robot built through a Spike Essentials kit, and it has a flat back. And look at where I am. I'm lined up on those two lines in the center of the starting area, right? And I'm pressed against the back wall. Now, if you had big things sticking out, you could move further down to the left or the right, but just make sure you start in the same place. I'm suggesting you start yourself in so that 0 degrees will be left to right on the mat, not against the back wall, even though that's square, left to right on the mat. Later, we'll show you how to break your emissions into parts. We try to start each section pointing at 0 degrees if we can. This way, we can easily replace the robot on the mat to test just that section. We don't have to test the whole thing, okay? And now that we're using accurate distance measurements, you might be able to draw this whole thing, measure it out, and program it and put it on the thing, and it'll work fine. It'll get close instead of spending hours at the table eating up all that valuable time. I'm suggesting write it all down, plan it, and then do it. Okay, so the basic gyro navigation code. Again, we're going to wrap this into different variants. We're not going to use a separate my block just for this. Okay, we're passing the angle and speed are passed into the variant my block that uses it. So we're using angle and speed, but the local guy is going to pass it. First, we're going to set the yaw into gyro current angle. This is only on Spike because then you can see it on the screen. Okay. The next set 2 sets correction equal to the past angle minus the gyro yaw. So this is the difference between where we are now and where we want to be. Okay. And it's also a negative or a positive, right? And we set that into correction is now plus or minus the difference of the past angle we want between where we currently are. Now, the adjustments, we talked about those adjustments. Adjust drive, we talked about in line follow. Adjust gyro is a way of increasing or decreasing the response of the gyro. If your robot is heavier, you may need a stronger response. In fact, if you watch these robots move, you'll see them wiggle, even though they're doing gyro. That's because they're moving back and forth slightly between the gyro line, always correcting. Okay. Finally, we are, hang on. Finally, we're taking the correction, the calculated correction, and doing a plus or minus to the speed. Again, on the left side, it's plus the speed. On the right, it's minus. Okay. Now, we suggest that you do not, this does allow you to easily change course by changing the angle, okay? And when executed, a big difference, the robot turns aggressively to the new angle while still moving forward or reverse, okay? But you only pass a minus speed. The problem is we don't want you to go very fast turning. So we have a discussion about that. So here's an example of what that is going to do, right? Set the correction. So if my angle, my gyro yaw is -1, as I did in the beginning, I'm a little bit left, and the angle I'm passing is 0, meaning I want to go straight ahead. I'm going to say correction is 0 minus 1 is a 1. Speed is 30. Speed plus 1 is 31. Speed minus 1 is 29. So I'm turned a little left. The left motor is going to get 31. The right motor is going to get 29. I'm going to steer back to 0, right? If I'm a speed of 5, or my angle is 5, and the gyro yaw is 0, which means I'm going straight ahead, 5 minus 0 equals 5. The speed is 30. 30 plus 5 is 35. 30 minus 5 is 25. So the left motor is going to be 35. The right motor is going to be 25. I'm going to steer right 5 degrees to 5 degrees. Okay? Now, here's the big one. Minus 45 and I'm at 0. I got minus 45 minus 0 equals minus 45. The speed is 30. 30 plus minus 45 is a minus 15. 30 minus minus 45 is 75. So I'm going to steer aggressively left to 45 degrees. The problem with this is too much speed on the turns can cause the gyro to drift. Okay? So we'll talk about what our solution is. We'll do a demo here. Here we go. Okay. I want you to notice that every time it moves, before it actually moves forward, it turns. And it's turning at a relatively slow speed. Okay? It is turning and correcting, and then it moves forward. So now the distance is good. The distance is whatever the real distance is, and that has been proven out. As it goes through it, you'll notice the 4 steps. Do the truck, do the bridge, do shipping, and go home. All right, I'm going to run it again. Notice the waypoint. It hit that waypoint. And you'll see that it's correcting before it's moving. Here is that other drive. Now, this does not use the steer first. See how fast it's correcting? And sometimes it worked, but then other times it would go bad. Now, you might be able to speed it up. I haven't experimented, but you're going to experiment with it and see. I didn't have a arm on there. Now, that had the older code. So now here's EV3. This also has the older code. Again, notice how fast it goes, changing the angles. Now, this EV3 code also had pauses between each one of those steps. There's a reason. I'll show you that a little bit later, but you could remove those and this would have gone a little bit faster. Okay. Now, here's the variant. Here's the basic demo. First, we're going to do gyro turn to angle. This is the gyro turn to angle, the new thing I added in V2. It's designed to accurately turn to a requested angle. This could be a truly, I have a misspelling here, a truly proportional response when turning. We use the difference between the angle we want and the current gyro angle as the response. Unfortunately, as I said, we have found when turning too fast too often, we will corrupt the gyro. So I have to fix that. Instead, we're going to use a variable called gyro turn speed max. Okay, gyro turn speed max. And that's to be sure we do not turn too fast. And you can test different amounts to see if it's going to do anything to you. This has a default setting in the code. Okay, And that will be used unless you set it at the top, right? Smaller, lighter robots may need a lower minimum response. Heavier robots will need a greater one. The default I've been using now is 20, and you can set that up at the top, or you could set it here. Once you get this code, you could set up there in the code. You have to change it in your code over a run, depending on what's going on, right? All right, so let's go look at that. So here's my block. Gyro turn to angle, and I'm passing only angle. This is a big mind block. I'm going to break it up, and it isn't that difficult to understand. So I'm defining it to pass the angle. The first thing I'm going to test for is gyro turn speed max. If it's 0, then I'm going to set it to 20, right? So the first time I come in, it's now going to get a value. If you set it up at the top at the beginning of the program, it's not going to even do this because it's not gyro speed max won't be 0, and it'll ignore this, okay? As I said, we've decided not to use a proportional response as it turns too fast and the gyro drifts. Okay, here's the start repeat loop, right? Repeat until gyro yaw is between angle minus 0.05 and angle plus 0.05. It's very accurate. Read carefully and read it out loud. Okay. And the nice thing is if you read this just like it says, you'll understand it. Okay, so we're going to set the gyro current angle to gyro yaw, or the yaw. And we do that so we can see it on the screen. Then we're going to set the correction to angle minus yaw. It's the difference between where we are and where we want to go. Okay? 0 means we're nowhere, right? 0 means we're there, all right? Negative angle means we want to turn left to the angle. Greater than 0, positive, means we want to turn right of the angle, okay? This is all changed over time and recalculated every time it's looped through. Now, notice in the EV3 version, see what it says and how it says it? It's actually exactly the same thing at the top, only they don't have a fancy schmancy if blah between blah and blah, then a Boolean test. And by the way, those angled things that have the angles, those big green things, those are what we call a Boolean test. They have to result in true or false. Okay, look it up. All right. Now we keep moving. We're going to get a correction. Now we've set correction in the step above, right? Here we set the correction of where we want to be. Here we're saying if the correction is less than 0, then set a new variable called turn speed to gyro turn speed max times -1. Okay? That means we want to go left. Otherwise, set the turn speed to gyro turn speed max. We want to go right. Okay? Right? It says, look if correction is less than 0, turn speed to gyro turn speed max times -1. Set the turn speed negative. We will be turning left. Else, turning right. Okay? Why can't we use the higher proportional speeds? We learned that it's too fast. It's going to throw it off. You could delete this whole thing and use the other ones, but I think you're going to run into problems. Maybe you try it and see what happens, right? What happens if the robot has to turn with a heavy load on the mat and has to drag it? You can change the gyro turn speed max in the code to adjust this, but change it back later when you need to, okay? And you can experiment any place in the code, all right? So this is not all rigid. That's why these variables are there, to take on situations you might run into. So the last step is we want to set the motors to tell them what to do. So turn speed now has the motor speed we want to turn toward the angle. The plus or minus motor speed we want to turn toward the angle. So in start moving, we're going to use the motion blocks to move the robot. Set left motor to turn speed and right motor to turn speed times -1. As we know, -1 flips the directions, so that motor these motors are going to run in opposite directions, but at the same speed. The result will be the robot will spin in place, no forward or backward motion. So what happens if the robot runs into an object while it's turning and it stops? All right, the turn will never complete and the robot will stall. If you're concerned, you could use, in a tight spot, gyro drive by time using a minus speed and back away from the object, okay? Or you could create a custom My Blocks to fix this. And there's more to come on that in a minute. Okay, so you get it? If it's trying to turn and it hits something, you're stuck. All right, so instead of doing that, before you call one of those that uses the gyro turn by angle to angle, you can say gyro drive by time and just back up for a half a second and you're away from the object, or a little further. So now what's happening here is, let's do the math. We're passing an angle of minus 45 with a yaw of 0. And let's do the calculation. Minus 45 minus 0 is minus 45. The direction is negative. This is the only way I could show negative versus positive. So we have a minus 20 is our turn speed. The left is minus 20. The right, which is the turn speed times -1, is now 20. So we steer left at the defined speed. Okay. Now we're still going. We're turning. We're at minus 20 now. All right. Minus 45 minus 20 equals minus 25. Again, we're going negative. So it's a minus 20 is our turn speed. So the left motor is minus 20. The right motor is 20. We're still steering right at the defined speed. Minus 45, minus 47. That's what we call an overshoot. We went too far. It's probably not going to happen, but that's what would happen in a proportional response. It could happen. So minus 45 minus 47 equals 2. That's a positive number. So the turn speed is 20. So the left motor is 20. The right motor is minus 20. And this number 20 might seem like a lot, but when you watch on the robot, it's really slow, especially on the large robot. You might have to adjust these or adjust that turn speed for the smaller robots. I'm not sure that I think I did that. I think 20 was okay for the EV3, although it was pretty quick. Okay. The last one is minus 45, and the yaw we're at is minus 45. That means we're there. So the result is 0. So we're 0 across the board. Across the board, we stop. Okay? Really pretty simple. All right. So now we have, we want to go to an angle of 90. And the yaw is 0. 90 minus 0 is 90. Direction is positive. Turn speed is positive 20. So it's 20 minus 20. We steer right at the defined speed. Think about it. The left motor is 20. The right motor is minus 20. We're not going to go forward or backward. We're going to spin in place. Okay? The angle we want to be at is 90. We're at 42. 90 minus 2 is 48. Blah, blah, blah. Right? And keep going down. Oh. Right? Oh, 90 and 92. So we overshot again. Okay? 90 minus 92 is minus 2. We're negative. So the turn speed is negative 20. And we're going to steer back left to correct. Okay? You can manage this turn speed if you need to, if there's different things going on the robot. All right? But you're going to have to experiment. So now that we're done, we actually are done. We've set the motors and we're done. I found that if we don't reset our relative position and clean that all up before we start, we can run into trouble. So even though we reset it in the code after this, especially the distance one, it ran into problems because the robot was still physically moving, even though we said stop moving. And that can happen. Inertia, right? The thing is moving and it can happen. So I put in a loop here at the end of the gyro turn to angle. And it's basically looping and it's saying repeat until the relative position is 0, rounded 0. Round is a math function that removes the decimals. Okay. And so it's saying reset the position, set relative position to 0. And wait 10 seconds. What am I saying? I don't think that set relative position is supposed to be in there. Oh, yes. Yes. Set relative position. And then we wait 10 seconds. If we did not wait, whatever follows may not finish. And this is all incorporated in the gyro turn to angle, so you don't have to even worry about it, okay? Okay, so now the gyro drive to waypoint variant. So this is a variant of gyro drive wrapping the code that drives to a waypoint line. We pass in the speed and the angle. Here's the speed and the angle we're passing in, right? We pass the angle to gyro turn to angle. It does its thing, right? It gets us lined up, and then it goes into the repeat loop, okay? This repeat loop allows us to go through the testing to see if the line waypoint sensor is less than the midpoint sensitivity, reflectivity. Again, you may want to create your own variable for that called waypoint reflectivity or waypoint dark reflectivity, something like that. And you can correct these and set them up your own way so they don't use the midpoint, because that could be different. And I noticed that that was a problem. So you're going to have to correct that. Okay. Now we're setting the waypoint reflectivity to whatever the value is, and that shows up on the screen. Okay. I talk about it here. For example, optional global line waypoint stop reflectivity variable. You could use that, but you're going to have to go correct that in the code and understand it. And then down in here in the box, there's my basic gyro code. Okay. Here's the variant over time. Okay. Identical to the line follow variant, except the basic gyro code is here in the repeat. Here's the speed, here's the angle, and here's the time. And we bring down the angle here. Here's the speeds come down here, right? Now, notice this does not call gyro turn to angle. And the reason is, if that hangs up, we never move. So if you're ever in a position where you're up against something and you want to go by distance or something, you, because we now are turning first, the robot might hang up. And because of that, you may want to move away from the object, and you can do that using a gyro drive over time. Okay. You may want to use this when you need to push, right? Because if you're pushing against something, if you're using distance and you never get to the distance you want, your thing is going to hang. So you could use the gyro drive over time to push against an object and then back away a little bit from it. Now you're clear. Now you can use your other stuff to go and keep going where you're going. Okay. Okay. So this is the whole problem of why would I need gyro drive over time? Okay. For example, in this particular case, what you may want to do is use the gyro to go up, use the gyro drive by time. You're already pointed in the right direction. You want to go up and push the tower. Push that tower so that you remove the shipment from the ship. Because if you get to the end of the thing and you still haven't gone the right distance, you are going to hang up. Here's an example. And there's the code down below. Okay. You got it? The unloading of the ship mission from the last season used it in this video. Okay. Again, gyro over time does not use the gyro turn angle first to keep it from hanging. So you may actually want to call gyro turn to angle first, get it in the right position, and then call this thing, unless it's already in the right position, right? So you have a lot of options. But I have to point this out because I don't want your robots to hang. Okay. Gyro drive over distance. Same thing as line following, okay? We're not, right? We have speed, angle. Here we have angle and distance. But we use those same things we did where we're calculating relative position times the distance per degree, okay? Now notice that this does call gyro turn to angle first right here, and it passes the angle, right? All right. And the angle is coming in here. That's the angle we want to use. It's the same angle that gets used down here. All right. We reset the encoder, the measuring encoder, and repeat the gyric basic code until the calculated distance is greater than the distance we want. You can see the line follow distance discussion. We talked about that in pretty much detail. But essentially what we're doing is adding up the degrees times the distance per degree we calculated at the top, and that'll come out to be less than the distance. And unlike line follow, this does work in reverse. This does work at reverse speeds. All right, keep everything else positive, but it does work at reverse speeds. Okay. So let's talk a little deeper dive about the problem of hanging on stuff. If the robot is in a corner against something and you execute a drive-by distance with a negative speed, it's going to first try to turn to the angle, even though you're at a negative speed. All right. Since the gyro, so that's a problem. All right. Normally it's so convenient. I mean, all I have to do is call it and I'm good. Okay. Why not use gyro drive-by time to back away a little? All right. That might work, but you can't control how far it's going to move back. Okay. But that will work, but you can't control. I suggest you create a brand new custom block of your own called gyro drive just distance. You're going to pass it to speed, angle, and distance. And you're going to copy some code in there. I'm not telling you which, without the gyro turn angle as the first step. And all the other code is going to go underneath it. Okay. When executed, if you use a negative speed, it will reverse, but still maintain the angle. Try it and go slow until you're out of danger, and then you can go fast and do whatever you want. You can't go too fast in a turn because you may corrupt the gyro. Okay. After you are free, you could use the normal gyro drive-by distance to keep going. Okay. So I'm going to ask you to go ahead and create this my block if you need to. All right. A final few ideas. As I said at the top, I'm using a much more robust version of Pi. My examples didn't have it, but I'm telling you here, you want to do that. If you like, you can remove gyro turn by angle from gyro drive by distance and waypoint if it's not helpful. Okay. And you could always use them separately. All right. Gyro drive by distance will then turn quickly when you give it a new angle. But again, you could run into problems because of the gyro. All right. The gyro adjust at low speeds, 40 or lower, I have it set to 3 or 4. Gyro adjust is how aggressive I want the gyro to correct. Okay, that has nothing to do with the angles. It has to do with the aggressiveness that I want to push that in. If I have that set to 1, the robot kind of just goes straight. Sort of. It might go off a little bit. If I have it set to like 3 or 4, you can actually see a slight wobble in the robot as it moves up. And that's because it's moving, it's adding 3 or 4 to the motors to help the correction. It's giving them a little more juice to help the correction. And you'll actually see it kind of make a wobble as it goes, a very tiny wobble. All right. But you will notice that when I used the big robot, okay, at a high speed, more like 60 above, it induced an incredibly large wobble into the robot that killed it, and it couldn't move any further. All right. And if you look at the Spike Prime advanced base that I built, what I had to do is set this to 1 when I go home because I'm going at high speed. I set it to 1 when I'm going at high speed, so the wobble is not that great. It'll correct. All the corrections work, and it'll go very fast. Okay? So you can look at the going home portion of the using gyro for Spike Advanced. and you'll see that. You'll see that little wobble in there. Okay, putting it all together with gyro navigation. So this, for example, was my doing the shipment, right? Do the truck, do the bridge, do the shipping, go home. Those have all been renamed with the word demo in front of them. And this is on the EV3, not the Spike Prime, but it's a good way to show it. So the mission program, drop, ship, and do shipment, right? Drop the bridge and do the shipment. What you can do is use many mission parts with steps you build into your own my block, okay? Called do truck, do bridge, do ship, and go home. You can put a 1-second pause after they run or just before they run and set an indicator to see what's going on. We've already talked about that. But the 1-second pause is there so you can see it stop, all right? And that you can use while you're developing, all right? If possible, when using gyro, these parts all start and stop at 0-degree yaw if possible. This allows you to easily test each part individually, okay? Then, 2, you change the mission program so that only the my block you want to test runs. Place the robot where it should start or in the last step ending position. A good guesstimate is good enough. Now test that my block until it's consistent, and then move on to the next my block, remembering where the other one left off, okay? Once they're all tested, remove the final pauses and do the final check, okay? And you will have to only make minor adjustments to get it work. Again, I think a lot of this can all be done on paper without having to use any computer, and your time at the table will be a lot less. In fact, I suggest you do the running around so you know that it's going to be where you want it to be, and then put all the attachments on and figure out what you're doing in between these steps, okay? And again, pat yourself ever so gently on the back because you did a good job. So here's do truck. Now you'll notice, right? Here's the first step. Here's all of the things in the first step. I'm pausing a second and the lights are green. And notice I have it lined up correctly, squared up on the spot I want. Okay, that was the end of step 1. Now notice where it stopped. Remember, it's hitting the yes, it was hitting a gyro waypoint. There it is. So it stopped squared up at 0 degrees right on that line. That's a great place to start your next one, right? You should be able to replace it. Remember how far it was away from the line, okay? So here's do bridge. Notice where I have it. It's sort of between the white and the black right there, right? The wheel is just on the black line, right? But it's squared up right against that that line, and it's perfectly square at 0. Now I'm going to do the bridge. Notice this waypoint showed us where to hit this. All those other measurements are somewhat accurate. Going back, I believe it also used a waypoint. Yeah, there it is. Drive line to waypoint minus 40 sets angle 0. So it did actually go back using a waypoint. Okay, so it did the bridge. Now we're going to move on to the next step. And notice where it is. It's in the same spot. Now we're going to do the shipping. See where it's lined up? Okay, it's done with the shipping. Now notice, this is not using the version 2, so it's not turning first and then going forward. It's using the older version. And if you decide you want to use that, you can. Just remove my turn by angle, and you can do it. Move it from the gyro drive by distance, and you can use the old one. Again, I'm worried about the gyro breaking out, okay? Because sometimes it does that. Actually, it turns out the EV3 seems to be better than the Spike Prime. I know people think that's a heretic, but I've seen it, and it seems to be that way. Finally, we go to the last step, which is go home. So now we're here. You kind of get it set where you want, and you just say, all right, go home. Now notice how fast it's going. Minus 100. That's as fast as it could possibly go. And again, this is not using the turn to line, okay? And I didn't have to reset the gyro adjust to let me go home because it's not going as fast. There we go. So that's how you can build your missions without killing yourself and actually changing the values and all that. It's really, really simple. It makes it really simple. So I just want to point you one more time back to the MAR FMA FLL Directed GitHub. You click that. You can get to this going to the FMA FLL Challenge info page. And on the FMA Challenge info page, the MAR Tools mailing list is on there. And I want you to join so that I can make sure I'm sending out messages only to those that are interested in getting the messages. I don't want to keep sending it to all the teams out there because they're going to kill me because I send too many emails. All right. Thank you very much for listening. Good luck this season and experiment and let me know how it's going. All right. If you have any questions, we'll meet on the weekly call, the Let's Be Frank call every Wednesday night at 7:30. Thank you very much. Good luck.